Hi, this is an example problem from Chapter 17 on interference of sound waves. Pause for a moment and read the question. So the idea in this problem is that we've got sound that is in phase. That means that A and B speakers are emitting sound waves that have crests that are coming out at the same time. They're emitting the troughs at the same time, and so they're in sync. Those waves travel and they come to the listener at point C where the two waves mix and they can interfere. And we're going to try to figure out if that interference produces a larger total wave that's louder or a smaller one that's quieter. To figure that out, we're going to go ahead and use the summary of wave interference here. It all comes down to looking at the difference in the paths, L2, L1, that the two waves need to travel from the second speaker to the listener and the first speaker to the listener. Depending on the difference in those lengths, if you have a zero difference or a whole number of wavelengths different, you're going to get constructive interference, which for sound waves is loudness. And if the lengths differ by a wavelength that is a half integer value of wavelengths, you'll get destructive interference. At the end of this video, I'll show you a little demonstration of why path length difference corresponds to this type of constructive and destructive interference. Okay, so the first thing we want to do is determine what are the path lengths from the two speakers to the listener where the sound waves overlap. So let me go ahead and draw the path from speaker A, straight line, to the listener at point C, and separately I'll go ahead and draw the path from speaker B, straight line, to the listener at point C. And what we want to do in this case now is just go ahead and label these. Doesn't matter which one. I'm going to call this first one here L2 from A to C, and over here I'll call this one L1 from A to C. And we want to identify those lengths so we can compare them. Well, L1's given to us. It's 4.8 meters. Now to get L2, notice that it is the hypotenuse of a right triangle, so we'll use the Pythagorean theorem. L2 in this case, we can write that simply as the square root of 6.4 meters squared plus 4.8 meters squared, which gives a value of 8.0 meters. Now we can go ahead and calculate the path length difference between paths L2 and L1. So path length difference is just the absolute value of the difference between these two paths. We don't care whether it's positive or negative, we just want the absolute value. But I've naturally chosen the longer path to go first. So if we plug this stuff in, we're going to end up getting here, let's see, 8 meters minus 4.8 meters, which gives us a value of 3.2 meters. Now, if this number here is a whole number of wavelengths, it'll be constructive, it'll be loud at the listener's ears. If it's a whole plus a half wavelength, then it's going to be destructive interference, it'll be quiet. To figure this out, though, we need to know what the wavelength is. In this problem, we haven't been given the wavelength, but we have been told the frequency and the speed of the waves in sound. And so we'll use the fundamental equation that relates speed, wavelength, and frequency to solve for the wavelength here, which is going to be the speed divided by the frequency. The speed is 343 meters per second, and the frequency is 214 hertz, but a hertz is a 1 per second, which allows us to cancel our seconds out. We'll be left with meters as we should be. And when we calculate, we come up with a value here equal to about 1.6 meters. Now let's go back here to the condition for these interferences. We're trying to figure out if this number can be written as an integer value times the wavelength or as a half integer value times the wavelength. Let's go back and inspect again. So we see that 3.2 meters here, well, this could be written as 2 times the wavelength, 1.6, meters. And so when we do that, we're identifying this guy here as our M, and this guy 1.6 meters as the wavelength. And so that gives us constructive interference in this case here. Now, a simpler way to go ahead and figure out if 3.2 is constructive or destructive is to take the path length difference, L2 minus L1, 3.2 meters, and divide it by the wavelength. In this case, the wavelength is 1.6 meters. Notice that if we divide by the wavelength, like here, right, we're going to be left with the integer value. And in this case, we just get 2. And so whole number integer values will be constructive interference, as we see here. If you get a whole number plus a half at the end, then it would be destructive interference. So seeing this, we can write this as this listener hears a loud sound due to the constructive interference. All right, I want to just show you for a moment why the path length difference does result in the different types of interference that we observe. So down here I have a little picture of a couple of speakers that are emitting waves. They're moving towards the right, and they have the same wavelength. And imagine that there's a listener, who's over here somewhere, and they want to hear. They're kind of listening. I'm not sure what planet they're from. But imagine that we go ahead and superimpose these two. If I put them right on top of each other, look at that. The difference between these two is 0, right? There's no path length difference. They're both coming from the same spot to listener. And as a result, the two waves match up perfectly because they're in phase, crests with crests, troughs with troughs. And the overall effect is to double the amplitude of the wave. Now, if I start to move these, so say I move it half a wavelength. There's half a wavelength there. Look at, there's a single half wavelength between the two speakers. Now the crests match up of one speaker with the troughs of the other, the low spots, and these two add together to produce 0 total signal. This is going to be a destructive interference, a quiet sound, and that's because we have 0.5 wavelengths, 1/2 wavelengths between them. If I go to a whole wavelength, let me go over, scoot one more bit over. There's a whole wavelength. Now all of a sudden you can see one sine wave between the two speakers, 1.0 wavelengths, an integer value, and they again match up. The peaks and the troughs match up and produce a larger total wave and a greater loudness. If we go to 1.5, again, we have interference that's destructive. If we go to 2, now we're going to have constructive interference again. And of course, if we look at this, we can see, here's the path length difference between them. 1 wavelength, 2 wavelengths. This is 2.0 times lambda, right? This is your integer value m, the 2.0. And we can see here, everywhere where the waves are overlapping, they are matching up to produce a larger amplitude wave. So if I added this together, I would be adding these two. I'd be getting a larger wave, something like this, right? And that's what produces, of course, you got to imagine the other one continues here, right? That's what produces the constructive interference when it reaches that listener.